Okay, so we're going to do an example here of continuous charge along a line, but rather than it being a straight line, it's going to be a circle. And so just to lay this out again, we've got our coordinates, and I've got another video that specifically shows the cylindrical coordinates. But I want you to imagine here what I've got is I've got sort of a bottom circle of a cylinder, and that we've got a coordinate system then where I've got a z-axis, I've got some s value, and then going around the circle I've got some phi value. And I want to look at, if I've got charge along that line, what would my potential be? And again, we're going to start with a simple case here, where we're going to look at the potential along the line that's over the center. So basically along the z-axis. And in this case, it makes sense to use a cylindrical coordinate system because the problem is set up in that way. So my point in space that I'm trying to find the field is some distance up above the center of the circle. And the charge is located around this circle. Not a full disk, just a hoop. So it's along a line. So first of all, I want to talk about what that density would be. So I've got some value for S. And so my S is the radius of this circle. Now, in general, S is the distance from the center, so it's the radius of, or radial distance you're there. I'm just going to leave it as a value of S. You might have specific problems where they might say something like a circle of radius A and a height of distance B or whatever. But again, those are just variable names. We're just going to leave it with the generic S and Z. Now our source charge, again, we're going to use the idea here of using primes for the source charge. And so the primes are along this one, which is why we're integrating over the primed variables as we go around. So to find that lambda, well, lambda is going to depend on how big our circle is. In general, it's the total amount of charge divided over the total length. And so it's some total amount of charge over 2 pi s, because that total length is the circumference of the circle. And I could make this an S prime just to make it clear that it's the source circle that we're using there. Okay? So I've got that value. And if it's a uniform density, which we're kind of assuming here, otherwise you'd have to be given some sort of function for it. We're not ready to do those ones yet. But for right now, I can keep it as just lambda. Okay, in the end, we'll use this as some simplifications as we're doing some other stuff. Okay, so now I got to figure out what my R is. Okay, And my r, again, just in terms of words, is the separation distance. And again, we're looking at the field point versus source charge. So I'm going to come back up to my diagram here, and I'm going to add another line in here. And I'm going to add it in a lighter color here so we know that it's not part of our diagram. But from my point P down to my point on the circle, that is going to be my separation distance. So that separation distance is the hypotenuse of a right-hand triangle, which has z on the bottom, or z on the vertical side and s on the bottom side. So for this particular problem, that r is going to be the square root of s prime squared plus z squared. And the z is not where the charge distribution is, so that's an actual coordinate. Just cleaning up my writing here a little bit. Now again, if I were to use my a and b, then that r would be equal to the square root of a squared plus b squared. Where I was using my circle of radius and my height of radius. And my DL, well, since my little incremental links are around the circle, I have to use a little incremental value here. And particularly what I'm changing is this part. As I move around the circle, I'm going around in phi at a set radius of s. So my incremental length for this particular problem is s d phi. I'm just going to change a few of my colors here just to make it clear when I'm using the other variables. So now I can put this all together. So I've got a 1 over 4 pi epsilon naught the integral of lambda s d phi over the square root of s squared plus z squared. And my limits of integration, I have to go all the way around the circle, so that's 0 to 2 pi. And this will give us the potential, a distance z above the center of that circle. And now we see where the beauty of this cylindrical coordinates comes in. I'm integrating over d phi. Everything else can come out of the integral because none of those things are changing. Lambda is a uniform charge density. S is the radius of the circle. Z is the height above the circle. 4 pi epsilon naught is a constant. And so when I solve this thing, I'm going to have lambda s over 4 pi epsilon naught, the square root of s squared plus z squared. And then the integral of d phi from 0 to 2 pi is just 2 pi. Now I'm going to carry this down onto a second page because again we want to use our idea of some of the limits and special cases just to double check what we've got going on. And remember from our previous page that lambda was equal to the total charge over the circumference. Right, the source charge is entirely contained on this circle. The charge is only on this circle. Our point in space is above it, but there's no charge up here. It's only charge on the circle, because this is a linear example. Okay, so some simplification in general of the equation. Well, notice I've got 2 pi and s, and so lambda 2 pi s, let me do this in a couple of stages here, is equal to q. So that v becomes q over 4 pi epsilon naught, the square root of s squared plus z squared. And once again, I could express this as just r. of course, since we know 1 over 4 pi epsilon naught is k, this reduces down to what I know. The potential above a uniform circle of charge is the same as if all of that charge was located at a point right underneath it. Now we can see this another way. If I think about my equation here and I take it and consider the case where Z is much, much larger than S. So I'm far away from this little circle of charge compared to the size of the circle of charge. Well, in that case, my S squared plus Z squared is basically Z squared. The S squared part doesn't do much. So again, my potential would be lambda 2 pi S over 4 pi epsilon naught, the square root of Z squared. And the square root of Z squared is the absolute value of Z. So it doesn't matter if I'm above or below, it's still based on just the distance I am. And you could leave it like that. Or we could once again say that this whole thing up on top is Q. Because as you move further out, that circle looks like a point. And while I don't have much room down here, when we did the potential, if I move to a distance of infinity, then that's 1 over infinity, and so the potential does go to 0, just like we expect it to. Because the potential should always drop off to 0 at an infinite distance out. So this example is a circle of charge done in cylindrical coordinates.